So for block S, we see that it's flat on its surface, which means that F of G, the downward force, and F of N, the upward force, have to be equal in magnitude. And there's no force pulling this way since it's frictionless and it's moving this way. So the only horizontal force is going to be in this direction. Let's label that T. For block H, there's a downward force, which we'll call FGH. There's no horizontal force in this instance. And since it's moving downward, that means that this downward force has to be greater than this upward force. So this is tension, because these are all the same string, so we can just call those the same force. So for part B, I'm going to split this into block S and H. So this is block S. The net force of S is just equal to T horizontally, or the line of motion, because the upward force and the downward force have no influence on the fact that it's going to be moving right. And Fs is also equal to the mass of block S times acceleration. So we can just set those equal to each other. The net force of the block H is FGH minus tension. The net force of block H is also equal to the mass of block H times acceleration. We can set these equal to each other because we want to isolate for A. So we really just want this A to be in the equation. Since we solved for T here, we can go ahead and substitute that into there. So we can just replace this here with the mass of block H times G. We're trying to solve for the variable A, so I'm just going to add this over so that the A's can be on the same side. Take the A out because we're trying to isolate for it, and then we can just divide both sides by the mass of both blocks so that we can cancel. So the final equation for A is the mass of block H times G over the total mass. Okay, so we're asked to solve for tension, and we already derived this equation that T equals the mass of block S times A. And we're also asked to use only the variables little m of block H, A, and G. So I'm seeing this equation that I want to use. And the reason why is because both of them have this term in it. So we can just isolate by adding this over and subtracting this over. And since these two are both equations for big M times A, we can just set them equal to each other. Because remember, the goal is to get rid of this variable. We don't want it in our equation for T. And then we can just take out the mass of block H to just simplify it. Okay. For part D, we have the equations for A and we have the equation for T. So let's just start off with what will happen to the acceleration when we increase only the mass of block S. So when we increase the mass of block S, the denominator will get bigger, which means that this whole term will be smaller. Acceleration will decrease. Further, we have equation for tension, which is this. The reason why I didn't choose this equation is because we already proved that when mass increases, acceleration will decrease. So we don't necessarily know whether or not the increase in mass will compensate for the decrease in acceleration and what that will do to the tension. So I'm going to use this formula because assuming that the mass of block H and that gravity will never change, only acceleration is going to decrease, because we know, again, that when m increases, acceleration will decrease. So acceleration will decrease, meaning that this term will be bigger because it's being subtracted by a smaller number. And tension as a whole will also become bigger. Okay, since it's a new picture, we're just going to use a new page. So the net force of block H is still going to be Fg minus T. And the net force of block H is equal to the mass of block H times acceleration. So we can set those as equal to each other. And Fg is just the mass of block H times gravity minus T. So let's just isolate for T. So we add this over, and we subtract this over. So the net force of S would be equal to tension, the force going in the same direction with the line of motion, but now there's also a force going against the line of motion because there's friction. So F of K. Since we solved for tension down here, we can just plug that in for T. And then F of K we can derive from this formula. So we can expand this a little, because we know that F of N is just the mass of block S times G. And we want to isolate for Fk, so we're going to multiply this up onto the other side. Solve for Fk. And then we can go ahead and plug that into this and subtract mu k times the mass of block S times G. Further, we also know the basic statement that the net force of block S will always equal to the mass of block S times acceleration. So we can set those two equations as equal to each other. So because we're trying to isolate for acceleration here, we want them on the same side, I'm going to add this term to the other side. We can take acceleration out, and then we can just isolate for A by dividing the total masses so that this can cancel out. So my final acceleration equation. Okay, so for tension, we're going to use the net force of block H, which is equal to the mass of block H. And the net force of block H is also equal to Fg H minus T. And we know that Fgh is really just the mass of block H, which is little m G minus T. Since these two equations are both the net force of H, we can set them as equal to each other. We want to solve for the tension, so let's just add this over and subtract this over to the other side. Now we're asked for an equation of T without the variable A, and we solved here for A, so we can just plug that in. And since this is a fraction, I'm just gonna try to combine it using a common denominator. So I can multiply this by the total mass over the total mass, because the total mass over the total mass is still 1. I'm not changing the value, but I do want to combine these terms. So this just becomes 1 fraction over the common denominator. Now I'm just going to distribute these terms into the parentheses. Since these two terms have the same value but opposite signs, we can just cancel them out. And we see that there is a common factor in both of these, which is little m times big M times G. So we can take that out. And this is my final equation for T. And we're going to use this tension equation to solve for G. If this was 0, meaning that it's frictionless, we wouldn't have to include it at all. But if that is a number, that is some number, it's going to make this entire numerator bigger, which means that T will be bigger. So in the presence of friction, T will increase. Okay, so for part H, let's start with block S. Since it is flat on the floor and there's no additional vertical force acting on it, we can label this as FGS and FGN, and they are equal in magnitude. It's going to the right still, so let's just label this T. But now there's a frictional force pushing it back, so let's label that FKS. Now though, there's also an additional block that's in front of it, and we know that while this block S, is pushing on block M, I'm gonna label this block M, it's also pushing back with the same force. So there is a force that we can call the contact force from block M to block S. For block M, so similarly to block S, it's flat on the surface and there's no additional vertical force being applied. So Fn of block M and Fg of block M are equal in magnitude. Now this time, there is no tension acting on block M because it's not actually connected to the string. But there is this contact force acting upon block M from block S. So contact force Sm. And there's also friction here. So there's a smaller force because it is moving right of friction. For block H, there's only two forces moving on it, which is FGH. And since it is moving downward, tension has to be smaller. Okay, for part I, this is moving as a system. So we can just treat it all as a system. The net force of the system would equal to the force going this way, which is Fg of H, minus all the forces that are moving in the opposite direction of the line of motion. So that would be the kinetic force of block S and the kinetic force of block M. And again, we see that tension exists and this contact force between block S and block M exists. However, the thing about it is that they cancel each other out. They are moving in opposite directions and they have the same magnitude, so they just cancel each other out, and we don't have to include them when talking about the system. We know that the net force on the system is also equal to the total masses times A. So we can just set those as equal to each other. And then let's expand it. So FGH is just the mass of block H times G minus Fk of S. So that would be the mass of block S times G times the coefficient of kinetic friction minus the mass of block M times G times the coefficient of kinetic friction equals to... Now we're asked to solve for A, so we're going to isolate it by dividing on both sides the total mass so that these can cancel out. Okay, and we're given the values of each variable, so let's just substitute those in. And if you plug that into a calculator, you'll get and we're just going to take the line of motion to be positive, so the acceleration is positive. So for part J, we're asked to find tension. So we can solve for the net force of block H, which is always equal to the mass of block H times acceleration. But in this case, it's also equal to the downward force, which is FGH, minus the upward force, which is tension. We know that the downward force is the mass of block H times gravity, and we can keep tension as is. Because these two equations are equal to each other, we can set them as such. And we're trying to solve for t, so let's just add this to the other side and subtract this to the other side. So now we can start to substitute. We know that m is 3, g is 9.8, and we solved for acceleration here, which is 2.5725. And we'll get 21.6825. So we're asked to calculate the contact force, which we named as SM, but since this problem names it MM, let's just call it that. Let's just label it that. So the net force of block S is equal to the mass of block S times acceleration. We also know that the net force of block S is equal to tension, that's pulling it rightward, minus the friction force of block S, and then minus the contact force of block little m onto block S. Now it's also important to note that the magnitude of the contact force from block S onto block M is equal to the magnitude of the contact force of block little m on block S. So we're going to try to solve for the magnitude of this contact force so that we can just solve for the magnitude of both. So since these two equations are equal to each other, we can set them as equal to each other. And we want to solve for this. Let's add this over and subtract this over. We can also replace FKS again with the mass of block S times G times mu. Now all we have to do is plug in these variables. We know T, we know M, and we know A. So Fm equals 2. So once you plug that into a calculator, you're going to get 13.0095. Since we solved for the magnitude of the contact force between block M on block S, we can also conclude that it is the same as the magnitude of the contact force on block S on block N. For part L, we can use common form in the y direction because we're given the displacement between the starting point and the point at which the blocks will hit the floor. So we're given h equals 20 meters. And again, h is just the displacement y. We're also told that it starts at rest, which means that initial velocity is 0, so we can just get rid of that term. And from here it's pretty easy. If we square root both sides, this will cancel. So VF is equal to square root of 2 delta y times a. Here we solved for a. So again, let's bring that down. And we have displacement in the y direction. So we can just go ahead and plug those in to solve for v. And you'll get around 10.144. So the magnitude of the final velocity is the speed at which the blocks are hitting the floor. So since we're trying to solve for t, we want a formula that involves t in it. So I'm going to use displacement formula. Since we have t variables that we can isolate. So we know that vi is equal to 0. So this whole term would be canceled out. And we're trying to solve for t. So we can divide displacement by a and multiply it by 2. And then we just square root both sides to cancel this out. And from here we can just substitute in those values because we solved for them already. We're told that displacement y is 20 and acceleration is 2.5725. Plug this into the calculator. We'll get 3.94 seconds. So finally for part N, we're asked to draw out the position versus time graph, velocity versus time, speed versus time, acceleration versus time, and net force versus time. So let's start off with acceleration actually, because it's the easiest. The whole time it was stagnant at 2.5725. We can call this time. And this is acceleration. In that case, velocity, since it's initially at rest, it will start down here at 0. And acceleration is just one number, which means velocity is increasing at a constant rate. Similarly, speed and velocity have the same magnitude, and in this case they will also look the same because at no point does velocity ever change direction. It's always in the positive line of motion, so we're just going to have them look the same. Since velocity is positive, position has to be moving in the positive direction, and acceleration is also positive, so we can conclude that the motion will speed up, the blocks will speed up as they go along, so position will look something like that. And for the net force of the system is just the total masses times acceleration. These will never change. And acceleration, as we concluded, doesn't change either. which means that net force will always be the same. It'll be a straight line.